All right, so just as a reminder, Chapter 7 quiz is on Schoology. If you haven't done so, get that work done, and you have until I think Wednesday next week. So I tried to give you time, and then with the shortened no school on Wednesday, plenty of time. So make sure you do that. So the last bit that we're gonna, the last chapter that we're gonna look at is chapter 8. And the first section of chapter 8 is on sequences, which are boring. Which really aren't part of the AP curriculum. Basically, a sequence is just some set of values that follow a certain rule. But what is AP material, this thing called a series, very much related to sequences, but this is like the cool uncle to the sequence. And then we'll talk today a little bit about a couple of tests that we can do with sequences. All right, so if we took an infinite sequence, maybe we have the sequence 1, 2, 3, 4, 5, 6.
Sorry, so this is 8.2 or 8.3?
This is 8.2. And tried to add them up. The sum is called the infinite series. And we use sigma notation, which we also used for integrals, to write it kind of in a shorthand way. Normally, we have values in the underneath and at the top of the sigma. That does say n equals 1, not n minus 1 here. This n equals 1, you just can't see I can see it, but it didn't project very well. So, and normally a sub n is some sort of a formula. It might be n over n plus 1. Yeah, I'm waiting for the guy behind you there. All right, so definition. We're not going to talk a lot about partial sums, but if I don't take the sum from 1 to infinity or from 0 to infinity, if I stop somewhere, then it's called a partial sum. And it's just the sum of the first however many terms I'm adding together. A lot of times, partial sums, sometimes you'll take like the first 10 terms and use that as an approximation sometimes of the entire sum. I cannot think of a time that I've seen the AP exam ask for a partial sum. Doesn't mean they never have, it just doesn't ring a bell for me. So we're not going to spend much time talking about other than to just define it. All right. So another bit of definitions. If the sequence S sub n is convergent and the limit as n goes to infinity okay, for some reason this should be the of the sum equals S. So it exists as a real number. Then the sum is called convergent. And we say or write a sub 1 plus a sub 2 plus dot, 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 equals S, or the summation of a sub n is equal to S, where S is called the sum. I wonder why they use the letter S. You know, sometimes mathematicians actually get it right. Sometimes you kind of wonder, though. And if that limit does not exist as a real number, we say the series is divergent. And so here is kind of the base of what we'll be talking about for the next couple class periods. As you finish writing that, I'm just going to remind you that next week we have a really weird schedule. Still cohort A, cohort B, but only 50-minute classes. So we can kick you guys out of here by 12:30. And then, you know, teachers get the plan for when everyone's back. So enjoy these last couple class periods where you have all of this space.
How many are in other class?
I don't know for sure. I want to say,
More than this?
I think 11 or 12. What's that? It just had to do with the kind of the way things worked out. I'm not in charge of scheduling. All right, so one important specific type of a series is a geometric series. And in general, a geometric series is just the sum, n goes from 1 to infinity, of a times r to the n minus 1. So your terms would go a plus a times r plus a times r squared plus a times r cubed. So to get the next term, you just multiply by that r. And we use r because it's a ratio. It's a term divided by the previous term. If you took AR and divided by A, you get R. That's your ratio. Every geometric series is convergent if the absolute value of R is less than 1. And the sum can be found by taking A, your first term, divided by 1 minus R. if the absolute value of R is greater than or equal to 1, the series is divergent and we cannot find the sum of that infinite series. All right, so here we go. Find the sum of the series 5, -10/3, or -10/3, I should say, plus 20/9, minus 40/27, and so on. In order to find the sum, we need to know what A is. What is A? Five. It's just the first term. That's A, 5. And then we need to know what R is. What do we multiply by to get the next term? And for me on this one, it's easier to see going from the second term to the third term, but that's just me. What's that? Negative 2/3. So the sum is A divided by 1 minus R. Five divided by 1 minus 2/3, that's the same as, so 1 minus negative 2/3. It's the same as 1 plus 2/3, so that's 5/3. 5 divided by 5/3, dividing by a fraction, we change to multiplication of its reciprocal. So 5 times 3/5 gives us 3 as the sum. Here we have another series written with that sigma notation. So we have the sum as n goes from 1 to infinity, 2 to the power of 2n times 3 to the power of 1 minus n. And we want to know, is that series convergent or divergent? So there are a couple of ways you could approach this. You could start just listing out terms, seeing if it's geometric, and then use our geometric formula. Or you could try to write it so that it's in that form, the sum of some value A times R to the power of n. That's the way I'm going to look at it for this example. So The first thing I'm going to do is look at rewriting this so that my exponents are just n's, or even n minus 1 wouldn't be bad. So this is the same as the sum. N goes from 1 to infinity. 2 to the 2n would be 2 squared to the nth power. If we take a power to a power, we multiply those exponents. And what I'm going to do is take the 3 and put it in the denominator. So it would be 3 to the opposite of 1 minus n, or 3 to the n minus first power. Everyone okay with the algebra going on there? Okay. Do just a little bit of simplification. You know, 2 squared is 4. Still going to leave this as 3 to the n minus 1. In order to get this so that it's to the same power, I'm going to rewrite my numerator. Four to the power of n is equivalent to 4 times 4 to the n minus 1. And now that I have those, what's that? This one? Yeah. Okay, so think about, 4 to the first times 4 to the n minus 1. If I add my exponents, 1 plus n minus 1 just gives me n. Okay? It's math magic. It's, all right. So, is that series convergent or divergent? I mean, clearly it's geometric, right? We have something times something to the power with an n in it. It's divergent. The absolute value of r is greater than or equal to 1. 4/3 is too big, basically is what that means. All right. One of the more interesting applications for geometric series are repeating decimals and writing repeating decimals in fraction form. So all repeating decimals can be written as an infinite geometric series, believe it or not. Finding the sum of that series then would result in finding the exact representation of that decimal, or the fractional representation of that decimal. I'm actually going to show you 2 ways to do it. I'm going to show you the geometric series way, which is kind of cool, but it takes a little bit of time. I'm going to show you a different way that uses algebra, which is the way I learned to do it way back when. Chiseling that on the stone tablet was a little bit easier than doing the geometric series way. All right. So we want to write 2.3171717171717171717 as a ratio of integers, or fancy way of saying write it as a fraction. So with the repetand, I think that's what it's called, the little bar above, 2.317 repeating. So I'm gonna, like I said, I'm gonna do my best to break this down as best I can. This is the same as 2.3 plus 0.017 plus 0.00017 plus, and that pattern would repeat. Okay. So the 2.3 has absolutely nothing to do with the geometric series. It's not part of what's repeating. Everything else is. So here we have 17 over 1,000. Plus 17 over 100,000. And if I wrote the next term out, it would be 17 over 10 million. And that pattern would continue. So this sum what are we multiplying by to go from one fraction to the next?
100. Or
1 over 100, right? Yeah. 1 over 100, right? So we start, actually, I'm going to write this a little bit, I'm going to say 0. We start with 17 over 1,000, and we multiply by 1 over 100 to the power of n. Right. So I can find this sum. It's geometric. A is 1 over 1,000. R is 1 over 100. Okay, so I still have, for that geometric series, A divided by 1 minus R. And 1 minus 1 over 100, I believe, is 99 over 100. Dividing by 99 over 100 is the same as multiplying by 100 over 99. Cancel out a couple zeros. This would be 2.3 plus 17 over 990. Now, the nice thing is, at this point, you could cheat a little bit and use your graphing calculator. You could do 2.3 plus 17 divided by 990 math fraction, and it would give it to you, and it would reduce it if it could be reduced. It's kind of nice. The 2.3171717, you can't just type that into your calculator, okay? So just be aware of that. This, let's see. This would be 23 over 10 plus 17 over 990. 2,300 would be 2,277. Multiply by 1,000, subtract 23. I think that's right. I don't know, try 23 times 99 once. All right, so 2294 over 990. And I think actually, they're both even, so it would reduce a little bit. So that's the using a geometric series method of converting from a repeating decimal to a fraction. What's that?
Number, why can't you just type in 2.31717? I tried it and it worked. I typed in 2.3171717.
Oh my goodness.
It worked.
Did I divide wrong? Oh, look at that. I divided wrong. That's crazy. All right, so as I said, this method I would never use personally. It's very clunky. It's very difficult. The method I would use, let's just assume X is 2.317 repeating. Now I'm going to multiply by 10 times the power of the number of digits that are repeating. So in this case, 10 squared, right? So 10 squared is 100. So 100x would equal, actually, let me, would be 231.717 repeating. Right, we're just moving the decimal place 0.2 places. But if I subtract, I would get 99x on this side. The 17 repeating cancels or gets subtracted off. And this would be $229.4 divided by 99. I don't know, in my mind,
That's a lot easier.
this is a little bit easier, right? Now, again, with your calculator, you can reduce this simply by using the decimal, right? You could put it in as 229.4 divided by 99, and the graphing calculator should simplify that, no problem. And we know that's going to be 1197 over 495. So either that whole full sheet of work that I did, or 3 steps and you're done. All right. Good with that? Like I said, I far prefer this method. And you will not be asked on the AP exam. Okay, it's highly unlikely that on the AP exam they will say, like on the free response section, write this repeating decimal as a geometric series, and they just won't.
No. Will they ask you to do the algebra method on the exam?
You might be asked to write a repeating decimal as a fraction on, say, a test that Mr. Gingrich or a quiz that Mr. Gingrich gives you, though. But again, I wouldn't specify you had to do it one way or the other. All right. I think this is the last one from 8.2. Called a telescoping sum. Show that the series, the sum as that should be, I shouldn't mix my letters, my variables. That should be N. There we go. So if we write out a few terms, right, that's kind of worked for us in the past. If N is 1, I would get 1 over 1 times 2, or 1/2. If N is 2, I would get 1 over 2 times 3, or 1/6. When N is 3, I get 1 over 3 times 4, which is 1/12, and so on. 5. So the first thing I notice is this is not geometric. I'm not multiplying by the same thing each time to get the next value. I have to multiply by 3 here, by 2 here, and there it's 5 over 3. But it's not the same thing every time. So we're going to look at it another way. If you remember when we talked about partial fractions, anyone getting the cold sweats yet? We could write 1 over n times n plus 1 as something over n plus another something over n plus 1. Look familiar? Yes, this is something that you will be required to know for the AP exam, this partial fractions thing. We used it for integrating, but it can be used obviously for other things as well. All right, if I multiply both sides by n times n plus 1, I get 1 equals a times n plus a if I distribute the a and the n plus 1, and b times n. Yeah. So I know I don't have any n's on the left-hand side. So 0 would have to equal a plus b. That's the parts with the n's. And 1 would have to equal a. So if a is 1, what is b? Negative 1. So my sum of 1 over n times n plus 1 is the same as the sum, n goes from 1 to infinity, of 1 over n minus 1 over n plus 1. And now you will see why it's called a telescoping sequence. When I plug in 1, I get 1 minus 1/2. When I plug in 2, I get 1/2 minus 1/3. When I plug in 3, I get 1/3 minus 1/4. And hopefully what you see is the half and the minus 1/2 cancel. And the minus 1/3 and the plus 1/3 cancel. And the minus 1/4 would cancel with the plus 1/4 in the next term. And everything cancels except for the very first term. So this sum is equal to 1. Pretty cool. I like it. So really the two series that you can find the sum for pretty easily, geometric and this telescoping series. Obviously, there's a little bit of work with the telescoping series, but it's not too bad. All right, so this is actually starts 8.3. If a series is convergent, then the limit as n goes to infinity of a sub n is 0. In other words, as we go further and further out with our terms, eventually the terms have to go to 0. We have to, at one point, not add anything anymore for the sum to be calculatable. Now be careful. What this does not say is if the limit as n approaches infinity of a sub n is 0, then the series is convergent. That is not true. But this is one test, so to speak, of whether a series is divergent or not. If you look at the limit and it doesn't go to 0, then you know for sure it's divergent. That we know. Let's see, what is that? I don't know, is that the contrapositive? I'm trying to remember my geometry. All right, a few other theorem type pieces. So if the sum of A sub n and the sum of B sub n are both convergent, then so are the series some constant times A sub n, the sum of the terms of the series, and the difference in the terms of the series. In fact, the way that you could write each of those, if you just take that constant times the sum of A sub n, that would be your sum. If you have the sum of series A and the sum of series, the sum of A sub n plus B sub n, that would be the sum of A sub n come on.
Are you trying to change the sum?
I'm trying to get it so that it's not superscripted. It's not liking me trying to do that. Yes, it worked. There we go. And then the difference as well, you could take the sum of A sub n minus the sum of B sub n. All right, so as I said, there is this test for divergence. If the limit as n approaches infinity, A sub n does not exist, or if A sub n does not equal 0, the series is divergent. So if I had the series n goes from 1 to infinity of n plus 1 over n, clearly my numerator is larger than my denominator, and we won't go to 0. So that would be a divergent series. All right, show that the series n goes from 1 to infinity of n squared over 5n squared plus 4 diverges. Well, to show that it diverges, I'm going to take a look at the limit as n approaches infinity of my definition of my terms in this sequence. And I get if I think about plugging infinity in, which is kind of a misnomer because infinity isn't a value. I would get infinity over infinity. It's not helpful. Okay.